Section 3.2, Logistic Regression as a Shallow Neural Network. We now position the logistic regression model as a deep learning model. However, as we shortly explain, it is not really deep, but is rather shallow, since it does not have hidden layers. This is the first instance in this book where we explicitly consider deep learning models in some mathematical detail. The general fully connected deep learning model is outlined in Chapter 5, and our presentation here serves as a shallow introduction. Note that the linear model of Section 2.3 can also be positioned as a deep learning model. We shed light on this too. Further, the multinomial regression model of the next section is a close relative of logistic regression, and as we show in the next section, it is also a shallow neural network. Logistic regression is an artificial neuron. Let us first represent the logistic regression model in equation 3.5 as this equation, 3.15. So we'll write y hat is some function sigma applied to the affine transformation B plus W transposed X, where we call this affine transformation, we call the result of that Z, and we call the whole thing y hat, we call that A. So that is common notation that we have throughout the book. Observe that in 3.15, we omit the subscript from sigma sig used in 3.5. 3.5 was the original equation of logistic regression in the previous section. We call sigma a scalar activation function, sometimes just activation function, which in the case of logistic regression needs to be sigma sub sig, but in other cases can be a different function. Section 5.3 is devoted to specific forms of such activation functions beyond the sigmoid function. At this point, let us just mention that a trivial alternative, the identity activation function, so this activation function, sigma of z just being z. With this identity activation function, the model in 3.15 is clearly just the linear model. The form of 3.15 represents what we may call a single layer of a deep learning model, a shallow neural network, or simply an artificial neuron. In this case, the vector inputs, x being elements of Rp, are transformed to a scalar output, y hat being an element of R. However, in general, deep learning models, as well as shallow neural networks, allow for vector outputs as well. The next section presents such a case. Observe that the artificial neuron is composed of an affine transformation, as we said, Z being B plus W transposed X, followed by a generally nonlinear transformation, A equals sigma of Z. This notation of using Z for the result of the affine transformation and A for the result of the nonlinear transformation is common in deep learning models and heavily used in Chapter 5. Note that the actual definition of an artificial neuron is sometimes taken as a combination of Z and A, sometimes just as the nonlinear result A, and sometimes as the computation mechanism defined by the right-hand side of 3.15, so the whole mechanism for computing this thing. Figure 3.3 summarizes the components of the artificial neuron, focusing on the specific sigma equals sigma sigmoid activation function. Let's look at figure 3.3. So what we have in the figure is the input, which is a p-dimensional vector, x1 to xp. We have our weights, w1, w2, wp. In this case, the weights are a vector. We do an inner product of the weights and the input, and we also add the bias, B. So at this point, this results in Z, in the result of the affine transformation. So we could have put a Z here. And then we pass it through an activation function. In this case, this is a sigmoid activation function. So this whole thing is sometimes called a neuron, or sometimes you just call the neuron the result A, which comes out here. And here in this figure, we also just see the form of the sigmoid function, but of course, the activation function could have been a different nonlinear activation function. And we have the output here, and y hat can also sometimes just be called A, especially if it is a neuron that then goes into other neurons in more advanced models. So that's all there is to it. A deeper learning model would have hidden layers based on composition of constructs similar to this equation 315 that we've just been speaking about. This would involve multiple Z and A values computed along the way. Thus, when there is a single layer, as in 3.15, the neural network is called shallow, and otherwise it is called deep. That's in chapter 5 and onwards. Logistic regression is the simplest non-linear scalar output shallow neural network that one can consider. Keep in mind that sometimes people call logistic regression also the case with vector outputs. In this book, we call that multinomial regression. Training logistic regression. We've already seen in 310, so we'll go back to 310 in a second, how maximum likelihood estimation position parameter fitting of logistic regression is an optimization problem. Let's just look at 310 quickly. So in equation 310, we just had that the solution of the fitting with the maximum likelihood estimation can be positioned as a minimization of this thing, which later we saw was a nothing but a cost function. Okay, so that was 310. We then saw that maximization of the likelihood is identical to minimization of the loss. So here's the loss represented again, with Ci theta defined via the cross entropy cost 3.12. So we defined the binary cross entropy. Importantly, when considered as a deep learning model or a machine learning model, one sometimes ignores the maximum likelihood interpretation of logistic regression and starts off with a cross entropy loss as an engineered loss function, which requires minimization. When statistical software packages are used to estimate parameters of logistic regression, statistical packages, this optimization is typically tackled using second-order methods. See section 4.6 for an overview of such techniques. In general, such methods make use of the Hessian matrix of the loss function or approximations of it. See Appendix A for a review. In contrast to statistical practices, in deep learning and machine learning culture, one often considers the number of features P to be very large, in which case standard second-order optimization methods tend to struggle computationally. Thus, when treated as a deep learning model, the default technique used for logistic regression training is gradient descent. Gradient descent was already introduced in section 2.4 in the context of the linear model, and variants of gradient-based learning are studied in detail in the next chapter as well. See sections 4.2 and 4.3. General deep learning models do not have explicit expressions for the gradient of C theta, given D, of the cost, and certainly not for the Hessian matrix. Hence, learning such models require computational techniques for gradient evaluation. The most common technique is a backpropagation algorithm described in section 5.4, which is a form of automatic differentiation overviewed in section 4.4. However, in the case of logistic regression, like the linear model, there are explicit expressions both for the gradient and the Hessian. Explicit expressions. we see these now. In the case of logistic regression, the gradient of the loss or cost with respect to theta equals b comma w, so that's an element of rp plus 1, is a vector in rd with d equals p plus 1. So the gradient is a vector for any point theta. It is denoted as the gradient and can be represented as the average of the gradients of each ci theta. Namely, the gradient of the whole thing is the arithmetic mean or the average of the individual gradients. This general relationship between the gradient of the total loss function, that's the gradient of the total loss function, and the gradient of the loss for each observation, like that, is common throughout deep learning. In the case of logistic regression, we have that the loss function for an individual observation is a binary cross entropy applied to the output yi and the expected, the label yi and the output of the predicted yi hat. We see E binary from equation 312. So that was a binary cross entropy. Let's see the binary cross entropy quickly again at equation 312. So here at the top of the page is binary cross entropy. And it takes y as the label, and y hat is the predicted probability. Okay, so you can think of y as something which is just within 0 and 1. Okay, so y is just going to be either 0 or 1, typically. And y hat is going to be anywhere in the interval 0, 1. Or sometimes you take it epsilon 1 because you don't want it 0 because you don't want to do log of 0. And you don't want to do log of 1 either. Log of 1 minus 1, which is 0. So you don't want to do log of 0. So sometimes you would take it as this interval. Okay, so that's the binary cross entropy. And it's a measure of the distance of y and y hat. It's not a distance in the full mathematical sense. Note that it's not symmetric in y and y hat. So we just reviewed binary cross entropy just a bit, and let's go back. We thus require expressions for the gradient of this binary cross entropy loss with observation label yi and predicted value yi hat. And yi hat is just going to be the sigma, the sigmoid of the affine transformation. That is, the gradient of ci theta is now we're using the binary cross entropy, is the gradient. We just took the negative from binary cross entropy out of this thing that I'm painting in green, and that was the inside of the binary cross entropy. Okay, so I'll put squares around the yi hat and 1 minus yi hat, where the gradient is with respect to the vector theta, which is b and w, b being a scalar and w being a p-dimensional vector. Now, basic differentiation rules and the structure of the sigmoid function gives us that the derivative of ci with respect to b is as follows, and the derivative of ci with respect to each wj is as follows, and that's for j going 1 to p. So this is from the just applying derivatives of the logs and the chain rule and the derivative of the sigmoid. Thus, combining these components, we can represent the d plus P gradient vector as, so then the gradient vector can be represented as follows. You take a vector of 1 here, and that gives you this first component that we had here in green for the B, and you take this vector of xi, and that gives you this second component, which you had here for each wj. So this is a p plus 1 gradient vector, where the first scalar expression on the right-hand side of 317 is a prediction difference for observation I, and the second expression is the vector of features for observation I, including the constant feature, right? So the gradient has this nice form where this is just your prediction difference, because keep in mind that all of this is just y hat I. Okay, that's nice. So we have an explicit gradient for logistic regression. Some benefits of cross-entropy loss. If one considers the problem of logistic regression training purely based on an optimization approach and not based on a maximum likelihood approach, then the cross-entropy loss could potentially be replaced by other loss functions, such as, for example, quadratic loss. However, it turns out that using the cross-entropy loss generally yields desirable loss landscapes. As an illustration, consider figure 3.4 based on logistic regression with synthetic data of a single feature. So P equals 1, and hence D equals 2. So you only have B and W1, right? But W1 is the only weight. The parameters to be optimized are the scalars B and W, or just W. In A, we use a square error loss, and in B, we use a cross-entropy loss. Okay. So what you see in the figure here on the left-hand side is the loss landscape, the function of the parameters B and W, with the A is your square loss, and your B is a cross-entropy loss. Notice how the right-hand side is so much easier, nicer to optimize, whereas the loss landscape here is much more crazy with a square loss. It is clear from this image that at least in this case, a cross-entropy loss landscape is more manageable to navigate for an optimization algorithm like gradient descent. In fact, in the case of logistic regression, cross-entropy always yields a convex loss landscape. Further details are in the next chapter. We actually discuss this when we discuss convexity in the next chapter. While other losses, such as a square error loss, will generally yield non-convex loss landscapes, often presenting multiple local minima as well as saddle points. Importantly, when considering classification or probability prediction problems, deep learning models that are more complex than logistic regression are still often easier to optimize using the cross-entropy loss than the squared error loss or other losses. In such more complex models, the neat mathematical convexity properties that logistic regression enjoys with cross-entropy are lost, and multiple local minima can exist. Nevertheless, computational and research experience has shown that in general, using cross-entropy is preferable. As an illustration of gradient descent applied to a concrete example, we return to the Wisconsin breast cancer dataset, now splitting the observations that we did in chapter 2. In N-train is 456 observations, N-test is 113 observations. We use a model with P equals 10 features. Okay, so then the number of parameters is the number of features plus 1, because 1 for the bias, so D equals 11, and learn the parameters via gradient descent with some arbitrary initialization. In doing so, we obtain trajectories as in figure 3.5. So what you have in figure 3.5 are iterations of gradient descent. In each one, you see the cross-entropy loss, so that's the loss of theta. And as we do this with each iteration, we are actually also computing the test loss and the train loss. That's a common thing to do. Okay, so you compute the test and the train loss. We have a monotone decrease here because of the convexity properties of logistic regression. That won't happen. Complete monotone decrease like that will not happen with more complex neural networks. And also we'll often use some variant of stochastic gradient descent. More on that in the next chapter. As we do this training, we also measure the F1 score. Remember, the accuracy is not a great measure to use because it's an unbalanced data set. So we use the F1 score, and we see the performance measure improve as iterations go forward. And that's it. So that concludes section 3.2. Excuse me, which is the first time where we've really seen notions of a deep neural network. I hope you enjoyed this video, and as always, leave comments below and let us know what you think. Thank you.